Good afternoon. My name is Bisharat Siddiqui. I am with Federal Highway Administration. I'm the division administrator here in Oklahoma, and I will be the moderator for the next two sessions. So welcome to the technical session, the second technical session. Before I get started, I want to take this opportunity to congratulate ODOT, the organizing committee, and especially Dr. Zaman for hosting such a successful virtual event. I understand there are close to 300 participants, so great participation, and I look forward to the second technical session herein. We have three great presentations lined up in the second session. And before I introduce the presenters, I just want to kind of go over the housekeeping items. Some of the Zoom features are disabled, and attendees cannot turn on their videos, microphone, chat, and raise functions are also disabled. For the question and answer features, there should be a Zoom toolbar. Please use this feature during the presentations to ask any questions. And we will field all those questions at the end of the session, but there will be an exception, just one exception, and that is for Dr. Puppala, as he has a class. So if you have any questions during his presentation, we'll just kind of like provide the opportunity to ask those questions right after his presentation. Teresa Stevens at ODOT, she's going to help me with facilitating some of the question and answers. So I appreciate that, Teresa. And for those of you who are interested in the professional development hours, SPTC will be using a log of attendees based on login and log off times. And they will be the ones who are going to be issuing those PDHs. So please make sure that you're logged with your individual account. And if you requested or need a PDH certificate and you do not receive it by November 3rd, please let us know. As far as the registration is concerned, if you have not registered by now, we would appreciate you doing that. It serves two purposes. One is we want to ensure that we have a good count of all the attendees, and we want to keep you included for future notifications also. So the registration link is in the program, and the registration will be open through tomorrow. We have set aside some time for our poster and video demo videos, and I will provide more details after this session for the set 2. So with that said, I want to introduce our first speaker, Dr. Anand Puppala. He's the professor and AP and Florence Wiley Chair at the Texas A&M University. In the interest of time, I'm not gonna read the bios. You can take a look at the bios that are included in the program, and please read them at your leisure. Dr. Puppala's presentation is on stabilization of expansive soils. He's gonna talk about the clay, mineralogy, and durability issues. So without further ado, Dr. Puppala.
Thank you, Basharat. Can you all hear me well?
Absolutely, we can hear you loud and clear.
Great, thank you. Again, as our moderator mentioned, the talk is about stabilization of expansive soils, clay mineralogy, and durability issues. In fact, the two other speakers that after this talk, both Soheil and Amy, we all are work in the similar area, and I have wonderful collaborations with them also. So it's very nice to have the whole thing. Unfortunately, I have a class at 1 o'clock, so I cannot be there. And I think, I just wanted to mention that. And I also want to mention Oklahoma Transportation Research Day, folks, for, Dr. Mushraf Jaman in particular, for giving me this chance to give this talk to you. And I think, this is a very timely talk. I've been working a lot on this research. This was done with Soheil a long time back with Texas DOT. And again, what you see is the building there is where right now I'm sitting right now, CIR. This is Center for Infrastructure Renewal, and next to the TTI. This is where all my labs are based here. Again, briefly, the outline is going to have these items here, expansive soils, infrastructure issues, and clay mineralogy, which is a little bit, I'll touch with this, and then I'll talk about the stabilization design, and then I go with the summary. Expensive soils, like I really like to call them expensive soils because anything you built on them is really expensive to maintain. Have damages are around billions of dollars per year. If you combine everything, including homes and home foundations, all the pavements, dams, and embankments, most of it is coming from your monazite clay, which is again like highly expansive. You see the structure. The water molecule here is what causes the whole thing. Just to give you an idea, if you look at the specific surface, every gram of this material has huge surface area. That means there's more room where it can attract moisture and holds them, and also has a high cation exchange capacity. So all these moisture holding capacities, if you convert them into swelling, all kinds of problems. You see the roads going up and down, even retaining walls, we are moving on the left-hand side, even though supposed to be a good backfill. Sometimes you have native soils as well. And you have all kinds of problems you see on the infrastructure here. Again, this is a very common phenomena in the Southwest states, particularly Texas and parts of Oklahoma. So this is a major issue for us here. And I also working with a lot of folks from dams and dam safety program. A lot of embankment soils are made of expansive backfills, so they crack. And when they crack, the first rain heat hits, it goes huge areas, a huge volume of soil gets saturated, and they can't stay any more stable configuration, so it starts sliding down. You see some of the crusts going down, and you see these things all along the embankments next to highways. And this is one particular one in Arlington, one of these, the whole sidewalls start completely, separated after a big major rainfall that came. So it's a major issue, and when we did this project with Paris District, Soheil remembers this picture, again, my PhD student, we have pushed it. This is a road that's only a few months old, 6 months if I recollect it correctly, and you have huge amounts of cracking taking place, and the cracks went when we measured it, and we were able to push up to 2 feet, but it could be a little longer. And this is on the travel lanes we're talking about. So huge of, most of this expansive soils issue comes from our cracking and then swelling. How do we characterize them? We do with the PI, which is not always easy because the two soils with the same PI are not exactly same type of expansive in nature. And we need to include clay mineralogy. That also gives some problem because it's a more chemistry. We always like to have thumb rule type of characterization. So this is where the problem gonna come. So we're trying to show a better way of characterizing, incorporating clay mineralogy, with some tests, because we spend more time or more money after failure than at upfront. So my hope is with this presentation, I will convince that we will do a little bit more on characterizing expansive soils, particularly focusing on clay mineralogy. That would help. In the case of stabilization, there are two important things, particularly the durability is very important. So that is also my focus for this study. So to give you an idea on this issue, if you look at these two soils are from Bryan, which is again in College Station, the other one is Fort Worth. They both have similar PI. If you look at the PI, it's around 29 and 31. But if you look at the liquid limit, they're different. So if you do use liquidity index, it may be better, but a lot of times we rely on PI. So as PI, these soils should be similar, but they're not. One of them has a kaolinite soil dominant. The other one is monazite. So if I use the same stabilization on these two soils, the soil that is rich with kaolinite is going to perform very well, whereas soil with monazite is going to have issues. And we have seen other soils like you see Paris and Forby, same thing, same PI, but different behaviors. And I think one of the things I want to mention is we do learn that we need to include clay mineralogy. So the two red bullets that tells us you have to improve your soil characterization, and then also when it comes to chemical stabilization design, you may want to include some durability aspects. So that is my takeaway points from this slide here. So looking at my time-wise also, so I'm trying to mention that one of the important thing is, as I said, is mineralogy. There are other factors that are also important, and I think unsaturated soil factors. So if you look at all these things, we have done a fundamental study with NSF where we looked at several soils and then compositional and environmental factors. And basically what we did is we took the soils and we measured the micro scale measurements, includes clay mineralogy and also porosimetry, and then soil water characteristic curves, which will tell you the moisture variation with respect to soil suction. And then we also measured with macro swell behavior, shrinkage behavior, and then we came up with some linking models. We felt this covers everything that we know going to impact our expansive soil. So even though it's a lot of extra factors, but this will give you a better understanding of what you're expecting when you put an infrastructure on top of these soils. So I show you, like, the soils are in general considered of a clay and non-clay fraction, as you can see here. And this is the non-clay, but the clay fraction is the one that governs your behavior. So in the clay, you have so many minerals, but I'm focusing on three predominant well-known minerals are montmorillonite, illite, and kaolinite. Just to give you, montmorillonite, is a very highly hydrating mineral. It has more specific area. So whereas kaolinite itself is a bigger particle in size, but you see the water layer around it is much thinner compared to a montmorillonite. So that's what explains you basically understanding the moisture holding capacity of these minerals will help a long way. So we studied several soils, and we looked at their PI material properties and also sizes. And also we did a lot of what we call as a clay mineralogy, estimation. We predominantly measured three things, which is CEC, cation exchange capacity, specific surface area, and potassium. And then we used this, formulation, and then also Microsoft optimized to come up with a clay mineralogy. This is how, this information is also available in the literature. And then you can measure these things by using 3 chemical mineralogy testing. And that will help you, understanding if you have a high montmorillonite, particularly if montmorillonite about 30% is already, you have to be, thinking that it's going to cause some issue. So what we did it, and then we also developed some models in the literature, you will find them. But basically, this will give you a better understanding than just simple reliability on your plasticity index. So we have showed that, understanding chemical behavior and also mechanical hydro parameters, which is your soil water characteristic, will help a long way in understanding, what this soil is going to do to your infrastructure. Because your infrastructure could be a 3 or 4 story building or a simple residential building. You have to know what is the stress you have and what is your swelling behavior you can expect from your soils undergoing moisture changes during its seasonal changes. So all these things will help a better design. So using this information, we went with a clay mineralogy based durability study for a TxDOT. This is a TxDOT project. You see, we have collected several soils. We basically identified the soils. In this case, like 8 of them, we took it to do the stabilization design. If you look at it, all these 8 soils, they have different types of mineralogy. The ones that are dominant with the montmorillonite, which is your smectite or a highly expansive mineral, is in red color. So we used those, we were focusing more on them. So the design, again, as I mentioned in the previous slide, we compared every one of them. I show you some results from our lab design. So one of the things we felt we need to do is include durability studies. So we did the ASTM D596, which includes wetting cycle and drying cycle. So once you stabilize it, you place them in different environmental conditions and then monitor the changes in their volume. And then what we did is at every few cycles, we tested them for strength to see how much strength is retained or how much we're losing. So basically, these are the durability conditions what we simulated in our lab. We did like 21 cycles, 0 cycles at 3, 7, 14, 21. We took the samples and ran the unconfined compression strength. So using this information, we were able to understand both strength and also volume change during the testing. How much are we getting? So just to give you an idea, the sample that is like here is what we call is one of the Fort Worth clay. The dominant mineral is montmorillonite. So if you look here on the top, obviously the top 4 show you untreated soil. Immediately, around like within a cycle, it started crumbling. It's no stabilization there, so it immediately failed. The second one is where we have stabilized with the lime around 6%. Around up to 10 cycles, it actually performed well and then started deteriorating, basically because of montmorillonite. So it survived around 10 cycles. And again, this is the soils that are kaolinite dominant. Again, you can see here, whenever we have kaolinite dominant, we were able to see the volume changes. Again, the untreated, the treated soil volume changes are up to 21 cycles are much smaller. So the smaller volume change footprint will tell me that I can actually stabilize the soil that are rich with the kaolinite is better, whereas with the montmorillonite, these volume changes are still like, expanding or going, and hence we start seeing the strengths going down. On the left-hand side, if you see unconfined compression strength up to 21 cycles, there is very little like loss. So that means any soil that is a kaolinite rich, we were able to maintain the strength, whereas soils that have montmorillonite, as I mentioned here, if I use for example, this black ones represent 6% lime, we have around 10% in the swelling and around 10% shrinking, which is very high. The samples around, like in this particular case, around 10 plus cycles, it failed. It did not even reach up to 21 cycles. But when we increased the soils in a lime with the cement, we were able to do all the way up to 21 with a little volume change taking place. On the left-hand side, with the lime treated, the samples failed with, as I mentioned, around around between 11 and 12. That's when it started failing. Whereas in the case of cement, we did see loss of strength, but again, it survived 21. But you can see the strength is tremendously low. So again, you have to see maybe we need to increase the stabilization here. So one thing we learned from this study is with the montmorillonite, particularly the amount of montmorillonite in a soil will play a major role in your design. So here, the 4 soils that I showed you, which are montmorillonite, none of them actually survived 21 cycles. Everything they survived is anywhere between 4 to 10 cycles. This is durability testing. And the volumetric swell strain and the total strains are also pretty high, which means they can cause huge amounts of movements that could cripple your infrastructure. And there's no strength retained, after so many. But again, please note that durability testing, what we do in the lab, is very aggressive. It's not necessarily same. So if 21 cycles is going to be a lot longer years of life under a paved surface. And whereas the soil that have kaolinite, we have actually went through a whole thing, and then the strength retained is much higher, which is pretty stable with all the factor of safeties you can build in. So we are actually able to survive completely without any issue. So if you see a soil that has same PI with a Bryan or a Fort Worth room, but the difference is the montmorillonite and kaolinite, that's what it will tell you. You may hear from one district or one location, hey, we never have a problems with that PI, it worked very well. Whereas the neighboring district or neighboring agency will say, no, we have issues with the same PI. That's because they're talking about different dominating clay minerals in their soil. So that's the one thing. Again, in our study, one of the FAR B district, he uses very small amount. This is the only one with kaolinite, but did not survive because the amount of lime used is very low. So when we use cement, this particular one actually performed well. So that is the one thing is important. So I'm just showing you one final summary chart. And one thing I can mention here is, we included this, look at in addition to all the screening you do, check the montmorillonite. Again, we put 50, in my opinion, maybe up to 40 or even 35 or 30, depends on that. You want to be careful with the montmorillonite. Then you can do the durability testing is important. In a lot of cases, what I noticed is in our studies, not only this particular study, but other follow-up studies, that sometimes the lime is not sufficient to stabilize this high montmorillonite soil. It's just a matter of time. It may happen depending on the whole thing. It can happen in 10 or 15 cycles, or it can happen 30 cycles. It will happen. So that's something you need to be careful. And again, in that case, adding cement actually provided extra unconfined strength, which hold the sample. So we have a lot less volume change. It actually helps well. So you may want to do combined stabilization design in those cases. So that's my main point from this study here. Again, I'd like to acknowledge all the agencies that fund us on this project. But also, again, I want to thank OTRD and Dr. Jaman for giving me this chance. And again, I hope with that is my last slide. I'll be happy to take a few questions, and then I will move to my class. Thank you again for the opportunity.
Thank you, Dr. Puppala. Great presentation. Appreciate that perspective. Teresa, do you have any questions? Or I don't see anything in the Q&A.
I don't either.
Okay.
Thank you for a great presentation, though. That was very informative.
Yes.
Thank you.
Well, Dr. Puppala will give another 30 seconds. If someone has a burning question, we'll give them the opportunity to ask that. Teresa, just checking in again. Any questions on your side?
No, sir, I see nothing.
One attendee hands up. I don't know what that means. But.
I think, yeah, I see a raised hand, but that function is not, that function is disabled. So if Mr. Ridley can type in the question.
So Anand, I think because I can unmute myself as one of the organizers, I want to thank you for excellent presentation. As you know, both Dr. Cerato and Dr. Miller are working in this topic, for a long time. It is really interesting to see that it's an old topic, but we still have so much to learn. So in your view, what do you think are one or two most compelling research that we need in region 6, Texas, Oklahoma, New Mexico, and so on? I cannot name any state in region 6 that do not have this problem.
That's a great question, Dr. Zaman. Let me mention it. I think Amy also has done it. I think even in her PhD study, she did some work on mineralogy. When we developed this study, we built with Soheil and me, we thought of including soil chemistry, which is not an easy thing because you have to include a lot of clay mineralogy. The first question that comes is, when the practice includes simple testing, when we ask them to do more, is it acceptable? Because that's what we were concerned. But when we saw the areas of forensic studies of failures, we know where the problems are coming. So we wrote this compelling proposal. Again, my lead PI is a Soheil. So when we wrote this thing, we really wanted to explore several districts, and then we looked at their practices. We did some surveys. One thing we learned is no two soils we all know this thing, but in our studies it's clear, no two side-by-side soils are same. They're actually different in clay mineralogy. So one of my PhD student, Dr. Chituri, is a faculty at Boise State. He did all the soil chemistry analysis, and then we developed the models, and then we also validated those models, and then we looked at the durability aspects, and we know the problem. So the best approach for an agency that deals with this type of problem is to really put a little bit of soil chemistry. We need to give that little respect to that, because you may think it's a same low PI, but if you have 20-25% monotonal, that's enough to cause enough swelling and enough distress. So that is where I think we don't simplify too easy with the expansive soil. We need to include a little bit. I totally agree. This is a type of work. We are all doing it. And I actually, believe it or not, I give a lot of talks. And when you asked me to talk about the same topic, I'm giving another talk in a couple of weeks on the same subject. I get a lot of invitations on this expansive soil because even now we have so many problems. That tells that we are fundamentally missing some important ingredients. And I hope that is one of these things is this monoclonal. Just measuring them will be helpful.
Appreciate that. And Dr. Zaman, thank you for that question. I do see one question in the chat box. And the question is there any significant effects of the type of lime used, such as the lime slurry, pelletized lime, or lime byproduct?
That's a very good question. We do use most of our, depending on the project, either quick or hydrated lime, but I do think it makes not that much difference. It's still the ingredients are similar, except probably the hydration may be a different factor. I personally don't think that's going to make that much of a difference. The cement, on the other hand, we felt the one reason why it made the difference is when you add cement, it's going to increase your UCS. In a swelling soil, particularly a soil that wants to crack under drying conditions, the one that holds it together is the strength, unconfined compression strength or pozzolanic activity caused by cement reaction. It will hold up together. It will only hold up to a certain extent. If this drying is too long or prolonged, you will have cracking. We know there's the micro cracking in cement treated soils too. So you need to see the type of the distress, how long, the duration. That's what causes the thing. But in my opinion, like the highly pozzolanic active material, at least increasing UCS in these soils. If you look at my study with the 6% lime and 6% cement, the cement actually held up. But again, you saw the degradation strength is not changed much. So that is where I think you may want to include some pozzolanic material or high pozzolanic active material to improve your performance.
Great, thank you. And one last question, I guess, another one in the Q&A chat box. What effects do sulfates have on durability?
That's a great question, because that's what I live on, sulfates. I know I actually just finished a study on high sulfate soils. Sulfates do have pose problems with both lime and cement. They're both going to cause these ettringite causes issues. We are looking at both moderate to high sulfates. We're talking about 3,000 parts per million to up to like 20,000 parts per million. We do think by mellowing or double mellowing operations, there's some ways we can mitigate it. But if you have very high amounts of sulfate, the reactions are inevitable. It just takes a longer period. That's one reason why in some ways a highway that is not had an issue, but suddenly after 15 years, you see a sulfate heave. That is because of that particular reason. It slowly grows and grows, and then at one point after 15 years starts moving, then you will feel cracking or heaving at the humps at the highway. So that's one part it will happen. And again, we try to cut down in those cases calcium component by adding a low calcium type of a fly ash. It helped a little bit, but again, it's only short-term studies so far. I didn't have 10, 15 years to see if that was effective. We have some test sections in Paris district. So we had to wait and see if there's an issue. Again, as I said, minute you say something, then suddenly something will happen and it'll humble you. So you want to be careful with this thing. But again, the preliminary studies is a mellowing and also low calcium fly ash are promising some good solutions.
Great. Well, thank you so much for making time. I know you have a class to attend. I have to go and teach. We wish you all the best, and thank you for being us with today.
Thank you, sir. Thank you very much, everyone.
Our second speaker is Amy Cerato. She's the professor of geotechnical engineering at the University of Oklahoma. And today she's going to be talking with us about using X-ray fluorescence to assess soil subgrade stabilization competency during construction inspections. And I see you online. So Amy, please take it away.
Great, thank you so much. It's great to see some of my former students online today. I hope some of this sounds familiar to you as we talk about soil stabilization. And today we want to talk about a way to better quantify the amount of soil stabilizer that we mix into our subgrade, because if we take care of our subgrade, it's the least expensive and best thing we can do to lay down a great pavement and have our roadways last longer and ride smoother. And so, as a lot of people on this call know, that a large portion of our transportation corridor construction projects use lime and other calcium-based stabilizer to reduce the soil plasticity, increase the soil shear strength, reduce soil compressibility, and reduce the soil's tendency to undergo volume change when subjected to variations in water content. So in simple terms, additives like lime render highly plastic expansive soils non-plastic and non-expansive. Determining how much stabilizer to add to a specific soil to achieve that appropriate and long-term soil parameter change is no easy feat, but we have guidelines such as the OHDL 50 and 51 and the ASTM D 4609, which exist to provide recommendations based on soil classification and the type of stabilizer that we should use. Today's talk is going to discuss a technique for assessing that soil stabilization competency and mixing adequacy. We're going to use X-ray fluorescence technology to do this. And the goal of this research project is to assist the state in improving the stabilized subgrade behavior by providing a fast, easy to implement method of testing stabilizer content and distribution during construction prior to the pavement laying, so we can correct any problems we see. In addition, we think this method provides a tool for forensic investigations where the presence or lack of additive in a stabilizer layer is in question. So, the amount of stabilizer to be used is, can you all see that? I'm sorry, I can't see, my Zoom is not showing.
Yeah, it shows up. We can see the presentation.
Okay, great, thank you. So the amount of stabilizers to be used is specified in the design phase, but currently we have no reliable way to check how close the field stabilization amount is to the laboratory design amount specified. Right now, we can do that rough check by collecting the bills of lading from the chemical stabilizer truckers and do a volume-based calculation based on the length, the width, and the depth of that roadway to be stabilized. Remember, which is designed for an 8-inch depth. In addition, we can use an easy indicator test that can tell us that stabilizer is present, but not how much is there. And there are a few existing methods to estimate stabilizer content in soil. The first is that titration process available through an ASTM standard D3155, but it's cumbersome, it involves lots of chemicals, and it's very operator dependent. And the next is a lime fixation capacity method. Another is the initial consumption of lime test, and then the unconfined compressive strength test. But this is very time consuming because it requires a test of the virgin soil and then a test after the soil has been stabilized to notice an increase in strength of a certain amount of PSI. So it's not exact science. In determining a procedure to use that will tell us just how much stabilizer made it into the subgrade prior to laying that pavement is timely and really important. So having a method available to easily tell how much stabilizer gets mixed into the subgrade is important, but also how well that stabilizer is distributed both spatially and throughout the required design depth. Will be an excellent way to improve our roadways. So if you look at this figure, you can see that the stabilizer content that was mixed in this particular roadway was not well mixed. So we've been working on this technology now for 7 years, and this figure is from one of the projects we worked on. This is just one example of a 50-foot lane along a stabilized roadway, and you see 4 rectangular figures here. It's like looking down the road. On the left is the top layer between 0 to 3 inches deep. Then it moves across to the right and down through the layer in 3-inch increments until we get to 9 to 12 inches. And you can see that there's very little stabilizer there, which is good since the stabilized layer is only supposed to extend to 8 inches deep. You can see the variability across and down the lane, varying from 25% in that red color to 5% in the top layer, which is the blue color, and varying between 5 to 15% between 6 and 9 inches. So this isn't really what we want our stabilized subgrade to look like, right? We want it to be homogeneous so that when we lay the pavement and the roadway is being used with traffic, we are getting a nice uniform ride and our roadway lasts for a long time. And so we may want to recommend a second pass at ripping and mixing, compacting might be warranted here to ensure the subgrade is adequately stabilized. But this kind of picture of the stabilized subgrade is what we want to provide the inspectors so that they can ensure that the subgrade is adequately stabilized. So, how does X-ray fluorescence work? X-ray fluorescence spectrometry can be used to determine the presence of various elements within soils, sediments, water sources, and even food items. With this XRF technology, it's possible to quickly conduct a multi-element analysis of a sample by exposing a sample of the testing material to an X-ray source. The elements in a sample emit a specific X-ray signature unique to that element, and by counting the number or intensity of the wavelength and the intensity of this signature, it's possible to determine quantitatively what elements are in the sample. In addition, the analysis captures elements in different forms, including ions, carbonates, oxides, and organic matter within the soil. So demonstration of the ability of this X-ray fluorescence analysis to measure trace elements in multiple applications is extensive in the literature. However, until recently, no information was available showing its applicability to measuring chemical additive content in stabilized subgrade soils. So even though many key federal and state agencies use this XRF technique, including the Department of Environmental Quality, the Environmental Protection Agency, and the Fish and Wildlife Management departments, for example, to qualitatively detect the presence of heavy metal contamination, this technique is rarely used to make quantitative measurements, most likely because the portable XRF doesn't have as extensive a calibration library that is available within the laboratory equipment. So our research team, though, has recently created an extensive standard calibration library specifically for stabilized soils, and we validated that not only the X-ray fluorescence technology itself, but the portable handheld X-ray fluorescence technology can accurately and precisely detect stabilizer content. However, and I'll talk about a little bit later, this detection capability is highly dependent on sample preparation, and we will tell you what type of sample preparation we think should be used in the field to get the best results. So in soils, the presence of elements found in abundance in chemical additives, such as calcium oxide, which is found in chemical stabilizers, can be measured accurately at magnitudes ranging from 0.01 to 100% of the total content of that dry weight. So in order to determine the stabilizer content, we need to know the amount of calcium oxide in the original soil, we need to know the amount of calcium oxide in the chemical stabilizer, and then in the finished stabilized soil. So we start this journey by sampling sites and sending about 50 grams of the virgin soil, 50 grams of the stabilized soil per sampling location, and then 50 grams of the chemical stabilizer from the job site to a commercial lab, where the lab melted the soil into a fused disc. We call that the whole rock analysis. And melting the soil and fusing it into a glass disc creates this homogeneous, stable sample that shows really great accuracy. But you know, it takes over 1700 degrees Celsius to melt soil. And so we're unsure of how that would occur, if we could, how we could do that in the field. And we're looking into that vitrification of soil possibility right now. 13 different elemental contents were determined, as well as a loss on ignition, and the resulting percentages by dry weight were provided by that commercial laboratory, and calcium oxide was used as the elemental compound to calculate the percentage of chemical additive in the field samples. This was done simply by taking the difference in calcium oxide between the treated and untreated soil and dividing by the difference of calcium oxide in the additive and treated soil. So we spent a lot of time and sending a lot of samples away to prove that this whole rock analysis, where they melt the soil down into a fused disc, it's proven to be an extremely useful tool for quality control applications or during forensics investigations, where that presence or lack of additive in a stabilized layer is in question. However, because it does require melting the soil and sending it away for testing, we wanted to investigate the portable handheld XRF units to possibly provide a method that could be used immediately in the field during the stabilization process. The portable field XRF unit seemed like a promising method to get a fast and accurate measurement, as well as that spatial homogeneity assessment of the stabilization of a subgrade before that pavement is laid. So in order to make portable field XRF units viable for construction projects, we had to investigate several different independent variables in order to determine how much effect these variables had on the results. We have combined manufactured laboratory samples and field samples from around the state on ODOT construction stabilization projects to refine and record the most efficient yet accurate sampling and testing procedures for assessing subgrade stabilization content and distribution. Specifically, we want to optimize the sampling and soil processing protocols for efficiency and accuracy in the field if this technology is to be implemented by industry, including contractors and construction inspectors. In addition, this technology has been shown to work exceptionally well in determining the sulfur content in the soil. So we're interested in using that in including sulfate-bearing soils to determine the accuracy of detection, and we're currently working through that right now. And this research builds on the promising results of previous testing conducted by us that looked on the effect of several variables, including sample preparation and detection techniques and the accuracy of the measurements. And we hope that very soon we can implement this type of technology into the ODOT specifications for construction. So one variable that we have found to make a profound difference in the results is sample preparation, specifically particle size. When we tried to use the portable XRF directly on the stabilized subgrade, we didn't get great results. And this is because of the particle size. So the variable particle sizes of the unprocessed field soil on the surface did not provide enough accuracy or precision. And so we noted that while we could still use this in the field, we'd have to do some sample preparation in the field in order for the accuracy of the portable XRF to be meaningful. And the samples can still be tested in the field, like I just said, but the soil must be sampled from the stabilized subgrade after already having tested the virgin soil in the chemical stabilizer. The sample must be homogenized, then crushed and processed over a sieve. And ideally, like I said before, we'd want to melt the soil because the fused bead eliminates any problems with particle size as it melts the soil down to a smooth glass disc. But generating upwards of that 1700 degrees Celsius in the field to melt soil may be problematic. We're still investigating. Then there is the pressed pellet that's made by crushing the soil down past a certain sieve size and using the pressure and binding agent, creating a hockey puck-like soil disc. Particle size is still problematic here. In addition, the pressed pellets would be difficult to make in the field. The sample preparation technique that we feel would be most beneficial in the field is the loose powder cup sample. And the soil should be crushed and sieved past at least a number 40 sieve, although the finer the better. And then the sample is poured into the pre-made sample cup with a proline film on top and then simply tested. And if you'd like to know how we test it, you can check out our demo video that we posted to the ODOT website as well, and that'll show you exactly how that happens. If problem areas are identified, then that subgrade can be remixed and compacted in a timely manner. And we're currently investigating the powder samples using those pre-made proline cups. And now I'll finish the presentation by just showing you some of the results that we've gotten. So on the left, you have stabilizer content by soil type. So you have a kaolinite, a montmorillonite, and a silty sand. On the right, you have the stabilizer content by different types of stabilizer. So we're measuring this as the whole rock analysis where we're melting the fused discs. And you can see that what we mix them to, which is on the x-axis, the actual content, 10%, 20%, 30%, is actually what we measured using the whole rock. It's exceptionally accurate. So I hope you can see that the whole rock analysis using those fused beads is now a proven method to measuring stabilizer content. And we do suggest that the Department of Transportation start archiving sample sets for each job for testing. But we also understand that the whole rock analysis takes a little bit of time, and we wanted to provide something that you could use in a faster method. And so here's the results from the portable XRF. And as you can see on the left, we have the stabilizer content, the portable, from the portable versus the whole rock analysis. we're using the whole rock analysis as the accurate count or the actual count. And you can see that there's a little bit more scatter. There's especially a lot more scatter with this silty sand. That's because it's a silica and it has bigger particle sizes. And these are just powder samples. So we're still getting that particle effect. But you can see, you know, it's pretty good. If it goes by soil type, so we take the silty sand out in the middle, you can see the kaolinite and the bentonite, not much difference, pretty accurate. And then on the right-hand side, this is the same portable handheld XRF versus whole rock analysis based on different types of stabilizer, CKD, fly ash, lime, and Portland cement. And you can see, you know, how close do we need to get in the field? Do we need to get to 0.1% or are we okay with 0.5%? If the design says 5% and we're measuring 5.5, are we okay with that? And so we do think this portable handheld XRF is a viable method for the field and quite accurate. This is just one more data slide.
If I may, we are kind of like pressed for time. So if you can just conclude your remarks.
I have 3 more slides. Anand took 30 minutes. You guys can wait 2 more minutes.
Okay.
Okay.
We'll do our best. So if you can, yes, please.
Sure. To reiterate the differences between using the whole rock analysis and the portable XRF technology, there are 2 figures I've shown here. On the left is the whole rock analysis, and on the right is the portable. You can see that the whole rock analysis on the left, most of the differences is between 0 to 0.2%, and on the right, there's a bigger scatter. And so we're still working on getting that accuracy more correct with that portable handheld. So the purpose of this research was to evaluate the use of XRF on stabilized subgrade projects for quality control and geotechnical forensic investigations. The whole rock was shown to be exceptionally accurate. The portable device was just a little bit less accurate, and we're working with that sample preparation. Particle size was the only variable significantly affecting the accuracy of that PXRF measurement. And higher accuracy was obtained when using the finer particles. So cultivating this technology aligns directly with the mission of transportation agencies to develop comprehensive, cost-effective, and imminently implementable solutions to critical infrastructure-related issues facing the transportation systems of the region and the nation. And we think that creating an accurate, portable, and efficient method for determining stabilizer contents will enable inspectors to enact improved quality control measures during construction, leading to more reliable and safer roadways. And additionally, we really do think that this technology will save time and provide more complete data during forensic geotechnical investigations, leading to cost savings and a deeper understanding of stabilization issues. And we think that this technology shows great promise in the pursuit of higher quality roadways at levels previously unattainable.
I appreciate that.
Thank you very much.
Thank you. Yeah, thank you so much for your presentation. Very informative. I'm going to move to the next speaker. We are going to hold on to the questions here for until Soheil's presentation. So our next presenter is Soheil Nazarian. He's the professor of civil engineering, University of Texas at El Paso. And his topic of discussion is a fresh look at developing practical balanced mix designs. Soheil, the floor is all yours. I think you are on mute, Soheil.
Yeah, that's the story of my life. Sorry.
That's
Can
okay.
you see my screen? Good afternoon, everyone. It's a pleasure to be here as a proud partner with OU, OSU, and the others on the Southern Plains Transportation Center. It's a pleasure to be here. Just want to discuss the balanced mix design from the work that we have been doing over here for the last 4 years for the Texas Department of Transportation. As always, we are very grateful to TxDOT for being such a good partner with us. I have some partners in this project, Victor Garcia, Luisa Barros, Dennis Vieira and Ahmad Abdallah. And as you see in the picture, a large number of our wonderful undergraduates. So this is a sizable project. So we got help from a lot of people. So what I'm going to focus on is just basically a brief overview of the balanced mix design concept, highlight some of the research that we have done in this area, and just share with you some of the findings. Basically, when we are talking about the balanced mix design, we are just trying to essentially look at the performance and come up with a mix that would resist cracking and resist rotting. And in this context, we use a Hamburg wheel tracking device for the rotting and overlay tester for cracking. We like the fact that it's a cyclic loading and gives a lot more information than some of the static tests. Essentially, when you look at the balanced mix design concept, that there are 3 ways of approaching it according to the Federal Highway Administration. You can do volumetric design and verify that design and make sure that it passes the performance. This is a little bit time consuming. It can be performance design, which it means that you're ignoring the volumetric information, or you can have a performance modified volumetric design, which you just essentially get the initial design information, and then you adjust the design if you do not pass the performance. So just to highlight, we are following the performance modified volumetric design, essentially because volumetric design is essential for constructability. So the main goal of the project were to, of course, implement balanced mix design. The 2 performance parameters, as we discussed, we try to balance is rotting and cracking. And the other option is looking at the volumetric and density consideration to maximize grain-to-grain contact and to minimize the influence of the binder. And as you see over here, the scale is not balanced anymore. We're just trying to take advantage of the grain-to-grain contact as much as possible. So the focus of the study today, we had some aspects, other aspects, but I'm going to focus on one given the time, and that's how we can work with the gradation and of the system so that we can pass the performance, again, overlay tester for the cracking and Hamburg for the rotting. And by maximizing grain-to-grain contact, you have a geotechnical engineer over here, so we are good at that, and we minimize the influence of the binder. So what we started with is a Bailey method. Bailey is an outstanding way of optimizing gradation, and essentially what they did, they broke the materials into 4 essentially 3 regions. One is the coarse aggregates. The second one is the coarse fraction of the fine aggregates, and then the fine fraction of the fine aggregates. Those are the 3 main regions, and just distinguished by a certain sieve that is a primary sieve that you consider. Okay, this was a wonderful concept. The concern that we have with the Bailey method, that Bailey method has been developed to give you the best performance, not in terms of the rotting or cracking, but in terms of volumetric conditions. How to optimize the volumetric condition, considering VMA and density as indicators of the quality, not the performance test. So we took this method and we adapted, and the first thing we wanted to do is to figure out what are the impact of the different aspects of these 4 parameters, primary sieve, and then the 3 gradation on the properties. So as we expected it for the different materials, we look at the dolomite, granite, and gravel over here. You can see that the optimum asphalt content, as the PCS is increasing, the optimum asphalt content decreases. This is something that, given the price of the binder, is followed. We looked at the VMA, but as the PCS is increasing, the VMA is decreasing for most material, and so on and so forth. So what would we do to the performance? So we started looking at several parameters with the same thing. We started looking at the tensile strength and how the tensile strength, for instance, changes with the PCS and the other parameters. We looked at the rotting parameter from the Hamburg, and we use a normalized rotting index, and anything above 1 is acceptable, below 1 is not acceptable. And you started observing. We started looking at the 2 parameters that we proposed. Instead of using the number of cycles from the overlay tester, there was some uncertainty in that. We get 2 parameters. One is the critical fracture energy. That tells you how easy it is for the mix to, when subjected to tension, to crack, to initiate a crack. And the second one is the crack propagation rate. This is a parameter that shows you when the crack was initiated, how long it takes for that crack to propagate throughout the height of the specimen. And for that one, if the crack propagation rate is less than 0.5 and now 0.45, it's good. And according to textile specification, we want the fracture energy to be greater than 1. So now we can start looking at this one and understand how the rotting, the strength, and the VMA are impacted by changing the properties. So we started with the control mix. We made it finer. We made it fine, even more finest, or coarser and coarsest. And with this radiogram shows you if you start with the control and you start making it a mix finer or coarser, how the other parameters impact. For instance, if I want to improve the rotting without impacting the strength or the VMA, I may go and make the increase the coarse fraction ratio. If I want to modify, for instance, some other parameters, you would see that they may have different interactions. So this gave us an understanding of what part of the gradation for different materials, how it impacts their performance. And then we have some other, we saw different trends, and we try to understand, and I am showing you 4 materials, or exact same mix design, but with the 4 different materials. I'm showing you the coarse fraction over here. And these guys have different crushing property, different absorption, different shape, and etc. But we are lump sum all of them within the same category, the same mix. Especially crushing, if it's crushing, if you have a control, you're just going through the finer gradation. And as you see, there is some impact when that happens. For crushing, we started looking at the British test, the aggregate crushing value. It's a British standard. And basically, essentially, you fill up a mold with the crushed aggregates. You apply pressure on it up to a certain pressure, and then you remove the material and you do the sieve to see how much change in the crushing you got. And one thing that we have found, that as the potential crushing increases, you are making the mix finer, and the optimal asphalt content goes down. And that may not be what you want. Essentially what we have done, we have gotten this knowledge, and it's gone into a tool, online tool, that we can essentially start from your initial gradation and then start playing with that gradation, and essentially make the mix to the coarseness that you desire within the specification, as well as, leave enough room for the binder so that you can get your volumetric in order. Let me show you some of the things that happen when you start looking at the gradation and try to get the grain-to-grain contact as opposed to the dense graded mixes that we work with. The first thing I would like to talk about is the binder source. So I'm showing you around 5 different binders. They're all the same PG from 5 different refineries. 1, 2, 3, 4, 5. And I have, as you see, the binder in the dense graded, traditional dense graded is impacting the performance, especially in the cracking. Anything that is in the green is acceptable. However, when we go and look at the balanced mix design with the good grain-to-grain contact, you see that all of them are within the acceptable. The rotting is impacted, but the cracking is not as much impacted. I show the wrap. This shows you the 3 different wrap percentage. All of them are original mix design. It's not that we replaced wrap with the mix. And you see that you can balance up to 38% by getting the grain-to-grain contact. Long-term aging, short-term aging, if you look at the traditional mix design, you see that 0.45 is the acceptable limit. For the traditional aging is significant, but when we balance and the grain-to-grain, the impact would be less apparent. Anyway, let me summarize and conclude. We say that balanced mix design that focuses on the gradation and type and source of aggregate is helpful to get a better performance. Adjusting aggregate gradation can, as I showed you, can improve the performance and make room for more binders so that the mixes would not be as dry as we have. When you get better grain-to-grain contact, the influence of binder becomes less important. So, and increasing the wrap content, we can increase the wrap content with the proper gradation and with the proper design to increase wrap without having any problem. And as I showed you, the balanced mix designs that we are advocating is less sensitive to long-term conditioning. With that, I appreciate your time and I will be glad to answer any questions. If you have any questions, my phone number is over here. Please give me a call or send me an email. I'll be glad to talk to you.
Great. Thank you so much, Soheil. Great presentation. Appreciate that. I am looking in the Q&A part, and there is one question for Dr. Cerato. And the question is, how quickly after mixing and compacting the subgrade treatments are the results obtained when using the portable XRF? And the second part of the question is, are the results immediate so the contractor can remix the subgrade or make any adjustments to the application rate if necessary?
So the results are immediate. You have to take a shot of the virgin soil, a shot of the stabilizer, the chemical stabilizer, and then immediately you follow the compactor, and you can take your sample, sieve it, and test it, and within 60 seconds have a number. So you don't have to wait because it's an elemental test. And then the second part of the question was what?
If the contractor can make adjustments, I guess, knowing the results, I guess, and I think you answered it.
Oh yeah, so once you know what it is and you've gotten that grid, they can go back and do the remixing to make sure that it's nice and homogeneous.
Great. Well, thank you so much. Teresa, do you have any questions on your side?
No, sir, I do not.
Okay. I see a question for Soheil. Some other groups are looking at balanced mix design without taking gradation into account. What are the pluses and minuses for those approaches?
Well, I mean, since early 2000, everybody has been working on the balanced mix design. I think there are 50 states and 50 studies at least. And I think there is nothing wrong with that approach. You know, as long as you can get the airways and get the volumetrics and get the performance, you're okay. But if you ignore one, the one that we don't like is when you do the mix design and you just start changing the binder to pass the performance. That one has issues with constructability, flushing, and things like that. But as long as you know you have the right airflow, especially VMA, so that it's constructible, and you have the performance test pass, you're good to go.
Great.
But
Thank you.
we know we think that you can get more out of the gradation if you put the effort to do the extra mix design. I think that it's beneficial to get the maximum from your aggregates because binder is expensive.
Great. Well, thank you so much for your perspective. Appreciate that. Again, let's give them a virtual thank you for making those presentations. There's a little bit floor time built into the agenda. So what we are going to do is we are going to do the set 2 for the poster and demonstration videos here in a minute. And we will reconvene at 1:50 p.m. So take a quick stretch break, coffee, whatever you need to do, check your emails and come back. And for those of you who want to look at the poster and demo videos, the links again are on pages 9 and 11 of the program. And if you have a question about the poster or a demo video, please use the Q&A feature. And the posters have a numbering system. So please, when you ask the question, make a reference to that poster number. And
Sharon?
yes.
Sharon, excuse me for interrupting, but there was a question posted late. It says, do you know if there is any research regarding the depth of stabilization 8 inches versus deeper?
Okay, thank you.
Forgive my dog in the background.
That's okay.
So that's
Teresa,
probably to me, I guess.
Yeah.
And so when we've gone out and tested, we found that often the mixing does exceed the 8-inch depth. So we find stabilizer down between 9 and 12 inches, but it is much less than up in the top 8 inches. So it's contractor dependent. It's how deep they're mixing, but it's I don't know of any research besides what we've just found going out and sampling in the field that it does occur below 8 inches.
Well, thank you again, Amy. Thank you again, Soheil and Anand, for your great presentations. This concludes the technical session 2, and we will reconvene at 1:50 p.m. Thank you again.